In this video, we are going to begin Chapter 10 by looking at simple harmonic motion. So before we get into simple harmonic motion, let's talk about springs. And springs often illustrate this idea of simple harmonic motion. But every spring is going to have a certain type of stiffness. You have a spring in your pen or mechanical pencil, and you also have springs in your car, the shock absorbers. And those two different type of springs have very different stiffness to them. It takes much greater force to bend the shocks in your car than the spring in your pencil. And so this stiffness, we call that the spring constant. That is talking about the force involved to stretch or compress per unit meter. So it is the units are represented in newtons per meter because we're talking about the force required to stretch or compress. So if we want to find the force applied to a spring, we can multiply the spring constant times the distance that it is stretched or compressed. Now, notice here in this diagram, both the force and the displacement here are in the same direction because this is your force that you are applying on the spring itself, not the force that the spring exerts on you. Using Newton's third law, though, however, we can look at that as being the opposite direction, same magnitude as this force applied. A quick practical example of how this is used is in a pressure gauge. Many of you may have used this to test the pressure in your car or bicycle tire. And a pressure gauge is simply a spring inside of a column that can be filled with air. And when we fill this column with pressurized air, it exerts a force on the plunger, and so we have the distance that it is forced out, and from that we can measure and see what the air pressure is. Now this just uses some basic calculation of pressure as force divided by area. We're not going to get into that. The main thing is what's the force applied here on the plunger if we have a spring constant of 320 newtons per meter and it's extended out 2 centimeters. So we want to know what is the force that that air is exerting on the plunger. So we can just put that into our equation, 320 times 0.02, and we get 6.4 newtons. This conceptual example here is a very simple one at the surface, but is very difficult to understand and remember. It's kind of counterintuitive. So let's think about a spring that has 10 coils. And so when I'm talking about 10 coils, means the turnarounds that we have in this spring. So how many times do we curl around in a circle? And we have 10 of those in a particular spring with a spring constant of K. Well, if this spring is cut in half, so half of 10 is 5, now we have 2 springs that are 5 coils apiece. What is the spring constant of each of the smaller springs? Now, you may think that, well, if K measures the stiffness, then that's just a quantity that's talking about the material itself and the way it's wound up in a coil, which is partially true. However, that gives you the misconception that it's constant no matter the length of the spring, and that is false. So looking at this, if we have a 10-coil spring that has a spring constant of K, it requires some force to stretch at a distance x. Okay, now these are just all arbitrary numbers. However, if we look at what's happening to 5 coils on the left and then the 5 coils on the right, when we're doing that, both sets of the 5 coils are also being compressed. However, that compression is half on the left and half on the right. And they're both experiencing the same force. The force that you apply on the right-hand side is going to be the same force that the right half of the spring exerts on the left half of the spring. And so if, say, this stretches 4 centimeters, then that means the left half is compressing 2 centimeters and the right half is compressing 2 centimeters. So that compression is split in half. So if that means that these 5 are only compressing 1/2 of x, whatever x may be, and the force is still the same, that means that the spring constant K here is actually going to be 2 times the original spring constant of K. And so you need to kind of process that a little bit and try to understand that. And I know it's confusing at first, but in short, if we cut the coils in half, we are going to then double the spring constant. If we cut the coils in a third, so say we had a 9-coil spring and we want to know what the spring constant is of just the 3 coils, well, that's going to be 3 times the original spring constant. Now, all of these springs, if we exert a force on them, they are going to then in turn exert a force on us, and we call that a restoring force. And Hooke's law tells us that this restoring force is going to equal the negative of K times X. We just looked earlier that K times X would give us the force that we apply to stretch or compress the spring. And this just tells us, well, it's going to be the same magnitude, K times X, it's just going to be the opposite direction. So this is telling us if we pull on a spring, we're exerting a force, say, to the right, then it's going to exert a force back to the left, away from or against the displacement in the opposite direction. If we then compress the spring, then we're pushing a force to the left, and so the restoring force of the spring back on this mass here will be to the right because it's going to oppose the displacement that was put on the spring initially. Now, in order to visualize this simple harmonic motion, we need to be able to rely back on some of our trig knowledge and some of our trig functions, okay? And not just the trig triangles, but the actual graphs of the functions themselves. So we're going to look at sinusoidal curves here, okay? So first, I want you to picture, we have a turntable here, and in this turntable is going to rotate in this direction, this counterclockwise direction. And on that turntable, we just have some ball that's fixed to the edge. And so it's rotating around and around. And we shine these lights down here to the left. And they're at the surface of the table. And so I want you to imagine what would the shadow be doing on this screen. And if we were to record the shadow on, say, some photosensitive paper here, what would that look like? Well, this ball is going in a circle. However, from the light's perspective, it's really just moving left and right. And what is the speed at which it moves left and right? Well, that speed is not constant. It's actually going to measure out this sine graph. And so it's going to speed up and slow down and speed up and slow down as it goes back and forth. And the curve that it actually maps out here is a cosine wave, which, remember, sine waves, cosine waves, they're pretty much the same thing, just off by a phase shift. And so this displacement, if we start with a positive displacement, a non-zero displacement, it is a cosine wave. And this cosine is based on theta, the theta that we turn around this turntable here. So our angle or angular displacement as we go around the turntable, that will determine our displacement from the center of the circle. And so this amplitude A is just talking about, well, how high, what is our maximum displacement and what is our minimum displacement? That's our value of A. So we need to go back to some of our phase changes and amplitude and all that stuff we learned in trig pre-calc to understand some of these functions here. And so our displacement function is going to be defined as A cosine theta. Well, what is theta? Theta is our angular displacement, and we know that's just omega times t, where omega is the rate at which we rotate, that's our angular velocity, and t is our time. So we can get a graph of displacement versus time, and it is in fact this cosine wave. If we look at a top view of this displacement, we may be able to understand this a little better. As we're at this position over here on the right, we're at our maximum displacement, and then the ball travels around the circle, and this displacement gets shorter and shorter and shorter until when we're at the top of the circle here, we end up at a displacement of 0, and then we go back out to our max displacement here, and then we come back and then go back and forth and back and forth. And so this displacement function is just a cosine wave of A, or amplitude, times the cosine omega t. We increase omega here, that means we spin more quickly. That is going to increase the frequency of our wave or decrease the period. Now these are terms that are coming back from trig that are going to have a physical representation, a physical meaning now in this unit. Amplitude is our maximum displacement, where frequency is going to be the inverse of our period, which is how long it takes to do one complete cycle. So to summarize with this, we have amplitude A, the maximum displacement, the period T, the time required for one cycle, so that's one cycle here on our graph, and the frequency we're going to call F, and make sure it's a lowercase f, and this is the number of cycles per second. We measure this in hertz. So if we talk about 120 hertz, that's 120 cycles every second. And a few things to rely back on from trig is that frequency is the reciprocal of the period, or period is the reciprocal of frequency, and omega is 2 pi times the frequency, or 2 pi times the time that it takes, 2 pi divided by the time it takes for one cycle. We've already done this. Last unit, we were doing this exact thing. We were looking at, well, it takes the Earth 365 days to go around the sun, so what is the angular frequency, or we called it the angular velocity. What is the angular velocity of the Earth going around the sun? A synonymous term to that will be the angular frequency. If we talk about the angular frequency, that is also omega. Now, looking at this same situation, let's talk about the velocity of the object. And I'm not talking about angular velocity, but the velocity going left and right. Those of you that know calculus, you know that, well, if you have a position function, what do you have to do to get the velocity function? Well, we just take a derivative of it. And so those of you that don't know calculus, fine, memorize this formula here. Okay, and so we know that the velocity function is then going to be negative vt times sine of theta, or negative a omega sine of omega t. Now, those of you that know calculus, notice the chain rule happened here, and we changed cosine to negative sine. So it's really just the derivative of the position function. But the omega had to pop out because we're taking a derivative with respect to t. And so this is our velocity function, talking about the velocity at which this particle goes left and right, left and right. And we have our maximum at a times omega, and we also have our minimum at the negative a times omega. Let's look at an example here. And in this example, we have the frequency of motion is 1 kilohertz, so that's 1,000 cycles per second. And the amplitude is 0.2 millimeters, okay? So that's 2 times 10 to the negative 4th meters. We want to know what is the maximum speed of the diaphragm that's moving back and forth to create this sound, and where is the where in the motion does the maximum speed occur? And so we're looking at this, and so we have our amplitude, and if there's no sound coming out, we're here in the middle. And then as the sound comes out, we stretch out to our max to the right, and then we come back and compress to our minimum to the left. And this is vibrating back and forth 1,000 times every second. Now, the displacement here is very small. The amplitude is very, very small, but it is moving very quickly as well. So if we want to look at the speed, well, we just use our velocity function. Vx is equal to negative a omega sine of omega t, and we're just looking for the max. So we just want the maximum, which is our coefficient here, and that's going to be a times omega, which omega is 2 pi f. Plug in our information. We have our amplitude, 2 pi, and our frequency, and we get 1.3 meters per second. So this thing's moving back and forth at 1.3 meters per second at its maximum. It's not always 1.3 meters per second, but its maximum speed is 1.3 meters per second. Now we want to know, where does that happen? Where is this a maximum? Well, the maximum speed occurs right in the middle. Once again, those of you that know calculus, you could actually maximize this function, and you could see, well, when does that occur? You could evaluate, well, that's going to be right here when the displacement is equal to 0. which just so happens to also be where the acceleration is equal to 0. So let's move into talking about the acceleration. And with the acceleration, we have the centripetal acceleration, but we also have this we also have this linear acceleration of moving left and right because the speed is changing, so there is acceleration. Well, the acceleration function, once again, is going to be another derivative. For those of you that know calculus, those of you that don't, just commit this to memory here. And so we get a negative a omega squared cosine omega t. And so our maximum is going to happen at this coefficient of negative a omega squared. And we can find our maximum by just taking the amplitude times the angular frequency squared, or we can determine when is it equal to 0 by setting equal to 0, all those things. So we have these functions now for position, velocity, and acceleration. Let's continue talking about the frequency of vibration, things that vibrate back and forth in this simple harmonic motion. And so let's say we have a spring that's vibrating back and forth, and so the sum of the forces on the spring is just going to be negative k times x, where k is the spring constant of that spring and x is the displacement moving back and forth. And so we know that the sum of the forces is equal to mass times acceleration, where acceleration is our acceleration left and right in that x dimension. Well, this position function, we can just say that that's a cosine omega t, and this acceleration function, we know that that is just negative a omega squared cosine of omega t, and do a little bit of algebra here, and we can see that, well, those cosines, they go away, and we get negative k times a is equal to negative m times a omega squared. Well, we can see that the a's go away, and we get this grand result of our angular frequency is equal to the square root of k over m. This is extremely important when we're talking about simple harmonic motion. Okay, so we want to vibrate something. We just move a mass that's on a spring, and we watch it oscillate back and forth. The rate at which it oscillates back and forth is dependent upon only two quantities: the spring constant, so how stiff is the spring, and what is the mass that is attached. So if we have those two quantities, we can find the angular frequency. One thing to notice here, this has nothing to do with gravity. This has nothing to do with how far we stretch it or how far we compress it. It only has to do with the stiffness of the spring and the mass that is attached. So the usefulness of this, we can actually measure the mass of quantities in a zero gravitational field. So in space, if we find objects and we want to know what is their mass, well, on Earth we have to actually measure the force due to gravity, and then from that we can interpolate what the mass is just by a quick calculation. But in space we don't have that gravity. The gravitational field is almost zero, so we can use this vibration to find the mass of unknown objects, or in this case the mass of the astronaut. A lot of times if you're in the space station for a long time, you need to keep track of your muscle mass and not lose too much muscle mass, so that way you're not paralyzed when you come back to Earth. So in this situation, we have a device that's consisted of a spring-mounted chair, which the astronaut sits, and the spring constant is 606 Newton per meter, and the mass of the chair is 12 kilograms. The measured period is 2.41 seconds. We want to find the mass of the astronaut. Well, we can do that by looking at the omega here, the angular frequency, is going to equal k over the mass, all inside of a square root. But remember, this mass is going to be the total mass of the chair and the astronaut. And so we solve for the mass to be k over omega squared. Well, what's omega here? This is 2 pi times the frequency, or 2 pi divided by the period. And we're given the period. In this case, it takes 2.41 seconds. And so we can solve for this and get the fact that the mass of the astronaut is equal to 77.2 kilograms. So an astronaut can pay attention to their mass to see, are they losing too much mass as they're up there, and they can change their workout regimen or whatever to keep their muscle tone so they can still walk when they come back to the Earth's surface. In future videos, we are going to continue to look at how these springs and these objects of simple harmonic motion can do work and how they transfer and exchange energy, but that will come later.